Thank you for coming. Welcome to the Chemistry 1406 final exam review. We're almost done at the end of the semester. So let me give you a little bit of a heads up on how this review will work. Yes, I do have a practice final exam, and yes, there are 120 questions on it. So there is no possible way that we are going to get through this entire thing in the 2-hour session that I have planned. However, I do want to focus on those things which you especially feel like you need help with, those things that you especially would like to review, and they don't have to be from this practice final exam. I only have this practice final as a source of questions for you if you don't have any of your own. But if you have your own questions, either from homework or from tests from your professor or from other practice tests, please feel free to bring those forward. You can even share those with me, and I will be happy to go over any of those questions. So how would you like to begin? Would you like to just start at the first problem and continue from there, or do you want to, or do you have any particular topic? Do you have any particular topic that you would like to go ahead and begin with? What specific calculations are you referring to? Any type of calculations, conversions? Okay, sure. Okay, let's go ahead and jump in and we'll do some conversion problem. Number 2 is a good example of a conversion problem. So we'll go ahead and start with this one. It says a nurse must administer the appropriate dosage of atropine sulfate to a 165-pound male patient. The dosage on the bottle is 20 milligrams for every kilogram of body weight. Each tablet contains 0.5 grams. How many tablets are needed to give the correct dose to the patient? Okay, so for a problem like this, a general rule for converting and conversion factors is you want to start with whatever is equal to what you're looking for. In this case, I am looking for how many tablets are needed for the correct dose. Okay? Well, the correct dose is based upon the weight of the patient. So, in this case, how many tablets, what's equal to the amount of tablets that I need to give for the correct dose? Well, it's based upon the patient's weight. So the patient's weight is what I'm going to need to start with. So, what are these other numbers? Forgive me, I did not get super great sleep last night, so I'm going to be yawning throughout the session. I do apologize. Okay, I have 20 milligrams for every kilogram. This is a conversion factor. Whoops. This is a conversion factor. 20 milligrams of medicine is equal to 1 kilogram of body weight. Which I'll abbreviate BW. Okay, I also see it says each tablet contains 0.5 grams of atropine sulfate. So each tablet contains 0.5 grams of atropine sulfate. Well, if that's the case, that's another conversion factor. 1 tablet is equal to 0.5 grams. And that's of the medicine. So I have 2 conversion factors given here. The 165 pounds is clearly not a conversion factor, which is another sign that that's probably what I'm going to need to start with. Now there are a couple of secondary conversion factors that would either likely be given to you or that you'd be expected to memorize. One of the conversion factors that would likely be given to you is the pound to kilogram conversion. So 2.205 pounds is equal to 1 kilogram. So now I'll take my 165 pounds and what's going to come on the bottom of this first conversion factor? It's going to go on the bottom of the first conversion factor. Yeah, pounds. So
Pounds.
Yeah, very good. Yeah, and feel free to use your mic. I mean, I love hearing people's voices. If you're not comfortable with that, feel free to text, but I feel free to use your mic too. So pounds, and then what can I convert pounds to here? What can I convert pounds to? Kilograms, yeah, very good. So I can convert pounds to kilograms. So you have the numbers above, it's 2.205 pounds is equal to 1 kilogram. That conversion factor is coming from here. So that's where this conversion factor is coming from. Okay, so let's then take a look at the next thing we need to convert. It's just kilograms. So kilograms, what am I going to need to convert? Kilograms has to cancel, so that has to go on the bottom. What can I convert kilograms to then?
Pounds.
Pounds. Well, I could convert kilograms back to pounds, but then I'd just be where I started, right? So you're not wrong that you could convert kilograms to pounds.
I'm sorry, I meant kilograms.
So no, okay, so here, yeah, so this is true. Milligrams of medicine, exactly. So I have kilograms here. Which of these conversion factors do I see? Keep in mind, this is kilograms of body weight, right? This is BW, body weight. I have to convert kilograms of body weight to what? Oh, I'm trying to get to tablets of medicine. So yes, I'll have to convert kilograms of body weight to milligrams of medicine, and that's where the conversion factor on the far right that I've written down is going to come from. Because if I look at this conversion factor, that's going to allow us to convert kilograms to milligrams of medicine. I've seen occasionally some students make the mistake of converting the kilograms to grams and then the grams to milligrams. But in that case, you have milligrams of medicine. I mean, milligrams of body weight, not milligrams of medicine. In this case, I have to be able to relate the medicine to the body weight. Yes, go ahead. Question?
Yes, for the where it says 2.205 pounds, do we always have to write it out like that to be able to work this out?
When you say write it out, do you mean like the 2.205 pounds equals 1 kilogram?
Yes, I know that sometimes I think people just use 2.2 instead of 2.
Oh, yeah, you can use 2.2, that's fine.
Okay.
I mean, that's totally fine. Sometimes they'll write 2.2, sometimes they'll be like 2.20, because the full number is actually 2.2046. So, I mean, like, yeah, I mean, it doesn't have to be perfect, especially in a case like this where you're actually looking at whole numbers. 2.2 is perfectly fine.
Okay, thank you.
Yeah, no problem. Okay, so then what's going to go on the bottom of the next conversion factor? I'm going to emphasize it's medicine. Yeah, so milligrams of medicine has to go on the bottom. That needs to cancel out. And that's the one consistent feature of conversion factors and dimensional analysis. Whatever was previously on top has to go on bottom. Now, what can I convert milligrams of medicine to that's going to help get me closer to my answer in tablets? Yeah, grams of medicine, exactly. So I'm going to convert milligrams of medicine to grams of medicine. And what numbers am I going to use there? Because I don't seem to have a conversion factor readily available above that tells me how to convert from grams to milligrams. So this is something that you're actually probably supposed to have memorized. Yeah, 1,000 what? Where does 1,000 go, on top or bottom? Yeah, 1,000 milligrams. So it's 1,000 milligrams is equal to how many grams? 1 gram, very good. 1,000 milligrams equals 1 gram. Great, I now have grams of medicine. So I still don't have tablets yet, so what unit's going to go on the bottom of my next conversion factor? Grams, yep, grams of medicine. And what can I convert grams of medicine to? Tablets, exactly. So, and the numbers are going to come from my nice little conversion factor here. And I will put 1 tablet is equal to 0.5 grams of the atropine sulfate, the medicine. So then all I have to do is multiply everything on top and divide by everything on bottom. And when I do that, what do I get? Yeah, 3 tablets. Very good. Now, just in case anybody was having trouble getting that, when you're doing these conversion factors, I've seen people try to do these calculations in a lot of different ways. But the easiest way to do that for these types of problems is literally to just multiply everything on top and divide by everything on bottom. And of course, you can ignore the ones. So if I'm typing this into my calculator, I would literally just put 165 times 20 times, well, I guess it's all ones then. So 165 times 20 divided by 2.205 divided by 1,000 divided by 0.5. And I would not use any parentheses. That's not only the fastest way to do it, but it's also the safest because you're least likely to make mistakes. If you start putting in parentheses and such, you can actually oftentimes group the parentheses incorrectly and therefore end up getting the wrong answer. Okay. So since you said conversions, another one I'd like to go ahead and do actually is number 3, because this is an interesting one. So which of the following is the largest mass? Well, the largest number is obviously C, but the truth of the matter is there's no way to know which of these is the largest mass without getting them all into the same units. So what I'm going to need to do here to convert them each to the same unit, I probably want to, since a lot of these are prefix units, centigram, milligram, nanogram, kilogram, I'm going to want to go ahead and convert them to the base unit because I think that'll be the easiest, the simplest conversion to do for each of these to try to get them into the same unit. So for the first one, I have kilograms. I can convert kilograms to grams. And the trick I'm going to show you, you don't have to use if you don't like it, if you don't prefer it. But I like to use this particular trick because I find it to be the most helpful. So for example, in this particular case, I always like to use a 1 in front of the unit with the prefix. The prefix is the extra letter in front of the base unit. The base unit is grams, and that tells you what type of measurement that you have. In other words, grams is a unit of mass. But the prefix doesn't tell you what type of measurement, it's just a numerical modification. So I'll put a 1 in front of the prefix unit, and then I'll put the numerical meaning of the prefix in front of the base unit. So kilo means 1,000. That's its numerical meaning. Kilo means 1,000. So 1 kilogram is 1,000 grams. And so when I multiply this, this is going to end up giving me 0.0041 grams. Now, 22 grams is already in grams, so I don't need to worry about that one. But I am going to have to convert the nanograms. So I'll go ahead and do that. In this case, nanograms goes on bottom, and I'm going to put grams on top. Now, where am I going to put the 1 in this case? Actually, I would put a 1 in front of the prefix. Like I said, you can do it the other way if you understand how to deal with that, but as a general rule, I find it's much easier. Put the 1 in front of the prefix unit, the 1 in front of the unit with the extra letter, and then what number does nano mean? What does nano mean? What number does it represent? Actually, it doesn't. Nano represents not 9, that would be nona. Interestingly enough, it's the same letters. Nona represents 9. Nano represents 10 to the negative 9th. Nano means 10 to the negative 9th. So in this case, if I multiply the top, divide by the bottom, this is going to give me 8.2 grams. Okay, I'll take now I'm going to actually pull this out, the 3 times 10 to the 3rd milligrams, and I'm going to convert the milligrams to grams. Once again, the unit that I'm canceling out, the milligrams is going to go on bottom and grams is going to go on top. In this case, if I follow the previous examples, where am I going to put the 1 in front of? Milligrams, yep. And then, what does milligram, or what does milli mean? What's the number? What number does milli represent? Actually, no. Kilo represents 1,000.
0.001.
Exactly. Milli represents 1/1000, or 0.001. And this is why I emphasize this, because it's really easy, especially if you start using 1,000 for milligrams and 1,000 for kilograms, to start switching those thousands and putting them in where they don't belong. But yes, this is 1,000, 1/1000th. Milli means 1/1000. So it's not wrong to say 1,000 milligrams equals 1 gram. So you could put 1,000 on bottom and 1 on top. But my personal preference is to go ahead and always put the 1 in front of the prefix unit to emphasize and understand the meaning that each prefix has a very specific meaning. Kilo means 1,000, nano means 10 to the negative 9th, milli means 1/1000th, or 10 to the negative 3rd. Okay, so so this is not milligrams, my apologies, so it's going to be 3 grams then. There we go. 3 grams. Okay, so now I'll do centigrams. Do the conversion here. CG. Where does the 1 go? Top or bottom? Yep, bottom. And what does centi mean?
100.
It actually does not. It means 1/100th. So if you think about, like, for example, a cent. A cent is not 100 of something. It's 1/100th of a dollar, right? And I guess you could make a case for century. A century is 100 years, and that's true. But that's not that cent, not centi. But yeah, centimeter. The centi prefix actually means 1/100th. Now you could say 100 centigrams is equal to 1 gram, but centi actually means 1/100th. So anyway, if I do this calculation, I get 3.52 grams. So which one of these is the smallest, or which one of these is the largest mass, rather? Not A, because remember, A was actually, yeah, not E. You guys are just guessing now. No, remember, you have to look at all of them.
B.
Yeah, B. B, because B is 22 grams. None of the other grams are even close to that. So A is only 0.0041 grams. C is 8.2. D is 3. And E is 3.52. 22 is more than any of those, so B is going to be the answer. Does that make sense? Any questions on that? Any questions on the process we used there? Okay, cool. What would you like to take a look at next? Do you want to do the conversion problem that uses density in number 4? What do you think? Okay, let's go ahead and take a look at that.
Yes.
Okay. So it says tequila has a density of 0.78 grams per milliliter. What mass will fill a 2.0 fluid ounce shot glass? And it gives the relationship 29.6 milliliters is equal to 1 liquid ounce or 1 fluid ounce. Okay. So whenever you're given density, you can use it as a conversion factor. So this is a conversion factor. I also want to know what mass will fill a 2 fluid ounce shot glass. And I'm given a conversion factor here. Of the 3 pieces of numerical information that I'm given, which one is not a conversion factor?
The 2.0.
2.0 fluid ounces, exactly. In other words, perhaps a better question to ask myself would have been, what am I looking for? I'm looking for the mass of tequila. So what's equal to that mass of tequila? What is the equivalent amount of that tequila? It's the 2.0 fluid ounce. I have to start with what is in some way equal or determined by what I'm looking for. I'm looking for the mass of tequila. That's going to be the same amount as the 2 fluid ounces. And that's why I'm going to start with the 2 fluid ounces. Oftentimes in these conversion factor problems, you'll also notice that the question part of the problem contains what you're supposed to start with. Not always, but many times. So what mass of tequila is in 2.0 fluid ounce? I start with 2.0 fluid ounce and then convert to the mass. So 2.0 fluid ounce. What's the first thing I'm going to do?
Maybe add 29 or multiply 29.6 by 2.
Okay, so I see what you're saying, but like in terms, what I would like to, you're not wrong, you are correct. So a good eye on that. What I would recommend doing is follow the units first. Whenever you're doing conversion factors, use the units to guide your thinking. So absolutely, just made that somebody said cancel the liquid ounces. Exactly. So I'm going to cancel the fluid ounces or liquid ounces by putting that on the bottom. And I can convert the fluid ounces to milliliters based on this conversion factor that I see over here. I'm trying to find my little cursor. Here we go. That little conversion factor over here that I see, this is going to be used for this. Try and color code it So that is 29.6 milliliters is equal to 1 fluid ounce. So now the next step is I'm going to go ahead and convert. I'm going to use my density. I'm going to put what unit on the bottom here for this next conversion factor, because I'm trying to get to mass. Milliliters, not mass, so I have to keep converting. Yeah, milliliters is going to go on bottom. And then what unit's going to go on top? What can I convert milliliters to? Grams. Yeah, absolutely. So milliliters to grams, and the density tells me that I have 0.78 grams per 1 milliliter. And in this case, I can go ahead and stop. This is kind of a mean question that they give you like the answer in all sorts of different crazy units. But I'm just going to go ahead and calculate this here to see if this gives me something that's going to follow one of those answers. Multiply everything on top, divide by the bottom, and what do I get? How many grams
46
is that?
grams.
Absolutely, very good. 46 grams. I don't have to worry about these other answers. 46 grams is the answer. Now your professor would probably give you all your answers in grams. They wouldn't do something evil like this. This is something like what I would do. No, just kidding. I would do that to you. All right. So let's go ahead and terminology stuff is important, and it doesn't take that long to go over. So let's go ahead and look at number 5. The melting point of a substance is an example of what? What type of property?
Physical property.
Yeah, it's a physical property. So in general, a physical property is anything that does not require you to use a chemical reaction to figure it out. So can I find the melting point of something without changing what it is, without reacting it? Yeah. But think of it like ice. If I put ice in, if I have ice and I put a thermometer in there and I figure out what temperature it melts, absolutely. It's still water even if it melts, right? Or it's still water even if it freezes, right? So I can figure out the melting point / freezing point of water without changing what it is. A chemical property is basically the ability to react in a particular way. That is the definition of a chemical property. Chemical property is the ability to react in a particular way. So I'm going to actually put that down here. The ability to react in a particular way, or with a particular substance. And then extensive property, this is a property, I don't know if you talked about extensive properties in your class, but we definitely do in general chemistry. An extensive property is a property that depends on how much of the substance there is. So what would be an example of an extensive property?
I guess if it was measuring like in grams or milligrams or ounces.
Yeah, absolutely. So the weight or mass of something is an extensive property. The more there is, the more it weighs, right? The volume is an extensive property. The more there is, the more you have. What about temperature? Is temperature an extensive property?
No.
No. Yeah, temperature doesn't depend on how much you have. It only depends upon the average kinetic energy of the particles. So temperature is an intensive property. Density, what about density? Is density an extensive or an intensive property? Does density depend on how much there is?
Yes.
Actually, it doesn't. This is the tricky part. The density is based on two extensive properties but when it's the ratio of them. So it's mass divided by volume, and because it's the ratio of them, it turns out that that ratio is the same no matter how much you have. So the density of 5 grams of gold is the same as the density of 5 pounds of gold. The ratio of mass to volume is always the same for a particular substance in a particular phase. So density is an intensive property. That's going to be important for the next question. So let's take a look at number 6. It says, which statement about water is true? What do you think? Read those 4 statements. Tell me which one you think is true. Apparently, I don't know how to use English. Got a few questions. Yeah. 8 grams of water has the same, B is the answer. 8 grams of water is the same density as 4 grams of water because density is an intensive property. It does not depend on how much there is. So that's definitely something that you could get. Okay. What would you like to tackle next? I know we did some review of the terminology stuff, and you said calculations was one of your concern areas. What other calculation problems or terminology type problems would you like to go over? For example, how are you with regards to naming ionic compounds, naming covalent compounds? How are you with converting with stoichiometry, grams to moles, moles to grams? Balancing equations? Okay, excellent. Let's go ahead and take a look at a few examples of those. Balancing equations. Here we go. So which of the following gives you the balanced equation for this reaction? So if I'm looking at this particular reaction, one of the things that I like to do is to list out my elements here. So for this, I'm going to list out K, P, O, Ca, and N. I'm not going to list O twice. Then I'm going to list the same elements in the same order, K, P, O, Ca, and N. And it's important that I do it in the same order so that I can keep track of them and I can compare them more easily. So once I've listed out my elements, I know how many each I have. Or once I've listed out my elements, I'm going to count how many of each I have on each side of the equation. Because the goal in balancing the equation is to basically uphold the law of conservation of mass, which means that mass is neither created nor destroyed in a chemical reaction. Therefore, the number of atoms of each kind that I have when I start has to be equal to the number of atoms of each kind I have when I'm finished. So how many potassium atoms do I have on the reactant side?
3.
Yep. How many phosphorus atoms do I have?
4.
On the reactant side?
Oh, I'm sorry. I was looking at the 4 on the oxygen.
Yeah, no, and that's a common. That's actually a very common thing that I see students do. So when you see a number like that, unless it's in parentheses, that applies only to the element immediately prior to it. So this
Gotcha,
is going
thank
to be.
you.
Yeah, no problem. So 1 phosphorus. So how many oxygens?
4.
Ah, this is the tricky one, because you have to keep in mind that you have to look at both compounds,
10.
right? Yeah, and this 2 outside the parentheses has to get multiplied by both things that are inside the parentheses. So 2 times 3 is 6, plus 4 is 10 oxygen. How many calciums are on the reactant side?
1.
1. And how many nitrogens are on the reactant side?
1.
Ah, actually 2.
2.
Yeah. Yep. You got to multiply that. So watch out for those parentheses. All right. Now, how many potassiums are on our product side?
1.
1. How many phosphoruses are on our product side? 2. Very good. How many oxygens are on our product side? 11. Very good. And how many calciums are on our product side? 3. And how many nitrogens are on our product side? 1. Very good. So now, whenever I'm going to balance an equation, I want to balance whatever's easiest to balance first. And the easiest elements to balance are going to be those that appear in the fewest compounds in the structure, or fewest compounds in the equation. So in each of these compounds, so I see potassium is in 2 compounds, all right? I'm looking at potassium. Potassium appears in K3PO4 and KNO3. Phosphorus appears in calcium phosphate on the product side and calcium nitrate on the reactant side. If I look at oxygen, I see that oxygen appears in every single compound. Phosphorus appears in 2 compounds. It appears in calcium phosphate and this. And nitrogen appears in 2 compounds as well. It appears in this one, calcium nitrate and potassium nitrate. So everything appears in 2 places except for oxygen, which appears in all 4, which means I can pretty much balance these in any order whatsoever, except that I want to save oxygen for the last. So if I just kind of go down the line here, I want to balance potassium. What am I going to have to do? I have 3 potassiums on my reactant side. But what do I need on my product side? What do I need to do?
Put 3
In front of what?
in front of the potassium.
Okay, so I can't just put it in front of potassium. I have to put it in front of a compound, right? So I'm going to have to change the coefficient. And the coefficient is going to be in front of the KNO3. Yeah. So this is going to be distributed. So this 3 is going to multiply the number of potassiums, the number of nitrogens, and the number of oxygens. So I will recalculate the amounts of each. I now have 3 potassiums, and I have 3 nitrogens, and I have 3 times 3, which is 6, or 9 oxygens rather, plus 2 times 4, which is 8. So 8 plus 9 is 17 oxygen. So now I can go ahead and balance my next one, and that's going to be the phosphorus. Notice I'm just doing it 1 element at a time. So if I'm balancing phosphorus, what am I going to have to do? To make the phosphorus the same on both sides.
You put a 2 in front of the compound?
Yeah, which compound?
That first compound.
K3PO4, yeah. So I'll put a 2 in front of K3PO4. Now we have to remember that these coefficients are multipliers. They multiply everything in front of them. So this is going to become Q times 3 potassiums, Q times the phosphoruses. So I'm going to get 6 potassiums. Now I'm going to have 2 phosphoruses. 2 times 4 is 8 oxygens, plus 6 is 14. 14 total oxygens. And so now run into another little problem. Anytime something previously has gotten unbalanced, I'm going to have to rebalance it. So what am I going to have to do to rebalance my potassiums? Because now I have 6 on the reactant side and 3 on the product side.
Do you change the 3 on the product side to a 6?
Absolutely, very good. That's exactly what I'm going to do. So I'm going to change the 3 on the product side to a 6. And once again, it's going to multiply everything in front of it. So I'm going to now have 6 potassiums. I'm going to have 6 nitrogens. And 6 times 3 is 18. 18 plus 8 is 26 oxygens. Okay, so now I have my potassiums balanced, my phosphorus is balanced. Oxygen's not balanced, but remember I'm waiting on oxygen until the very end because it's present in everything. So the next thing I'm going to do is calcium. So to balance calcium, what am I going to have to do? 3 on the product side, 1 on the reactant side.
Put a 3 in front of the calcium.
Absolutely, put a 3 in front of the calcium. 3 in front of the calcium nitrate, that is. And that's going to multiply everything in front of it. So I'm now going to have a total of 3 calciums. But then there's a 2 nitrogens already in that compound, 2 nitrogens already in that compound. So 3 times 2 is going to give me 6 nitrogens. And then there's 6 oxygens already in that compound. So 3 times 6 is 18. 18 plus 8 from the K3PO4, the 2 of those. 18 plus 8 is 26. I now have 26 oxygens. And now I see that my
Okay, so
calcium
I'm sorry. So you take the oxygen, the 3 times the 2, that's 6, and you times it by the 3 that you just put in front of it?
Exactly, because the 3 multiplies everything in front of it. Yep. So now I have 6 nitrogens, 3 calciums, 26 oxygens. Now I can see that every single one of my elements has the same number of atoms on both sides of the equation. So this is now balanced. So this is my balanced chemical equation, and I can look for which one of the answers corresponds to this balanced equation. And it looks like this is going to be D. So yeah, that's how you do it. Now, one could keep the polyatomic ions together if you wanted to. I know sometimes students ask me about that, but I honestly find that keeping the polyatomic ions together is not really a good idea because one, it really doesn't make the balancing any easier. If we compared it, it really doesn't make the balancing any easier. And furthermore, there are cases in which the polyatomic ions do not stay together, and therefore in those cases you cannot keep them together and still get the right answer. So I find that it introduces the possibility of making a mistake, and in addition to introducing the possibility of making a mistake, it also just it doesn't really make it any easier to begin with. So it's better, I think, just to go ahead and ignore or not, just to do it element by element. At least that's what I would recommend. Okay. What shall we go? What shall we take care of next? What shall we hit next? I'm open for any topic. Molarity. Good idea. Molarity and concentration. So let's skip ahead to molarity and concentration. Molarity. Where's molarity? Yes, Oz. Come now. Concentration. So Here we go. It says the concentration of sodium chloride in blood serum is 0.14 molar. What volume of blood serum contains 4 grams of NaCl? In a problem like this, when you're given molarity, you can use it as a conversion factor because molarity, remember, is equal to moles over liters. So I'm actually going to show you 2 ways to solve this problem. One is by using this particular formula. The other is they're using a molarity as a conversion factor, which I honestly think is easier, but for some students, they really prefer to use the equation. So let's start by using the equation, and then I'll show you how to do it with molarity as a conversion factor, and you can decide which one is easier. So in this case, well, to use this as an equation, I usually, as a general rule, like to list out my variables. I have molarity, moles, and liters. In this case, it gives me the molarity, that's 0.14. It does not give me the moles, and it does not give me the liters. However, does it give me something that I can use to find either the moles or the liters so that I can use this equation?
The 4.0 grams.
Mm-hmm. I can convert grams to what? I can convert it to moles. Yep, exactly. And so to convert grams of sodium chloride to moles, what do I have to use? I know grams is going to have to come in the bottom. So it cancels out. And I'll put moles on top. What allows you to convert grams to moles? Where do I look for those numbers? Atomic mass, or the periodic table, basically. So sodium has a mass of about 22.99, and chlorine has a mass of 35.45. And why do I know that? Because I am nerdy and have half the periodic table memorized. But if you don't, fortunately, you'll be given a periodic table. This would be 58.44. And so 58.44 grams is equal to 1 mole of NaCl. So then all I have to do is multiply the top, divide by the bottom, and what do I get?
I don't know if I did it right, but hold on, let me double check. I'm sorry.
That's okay.
Is it 0 point?
Yeah. So yep, that's what I got too. Yeah, 0.0684. Strictly speaking, it would only be 2 significant figures, but that's okay. We're going to keep a few extra sig figs right now because we usually don't want to round until the very end anyway. So this is our moles of NaCl. Okay, so now I have moles of NaCl, which is 0.0684 moles. So now I can go ahead and solve for the liters. Now to solve for liters, I can't solve for something when it's in the denominator. So if I take this equation, molarity is equal to moles over liters, and I want to solve for liters, I'm going to have to multiply both sides. Sorry, that's like sloppy as all get out. Okay. I'm going to multiply both sides by liters to get it out of the denominator. So liters is going to cancel out here, and I'm going to end up with the equation. The moles is equal to the liters times molarity. However, since I'm looking for liters, I don't want to stop here. I'm going to then divide both sides by the molarity to get the liters. So by liters is equal to the moles over the molarity. Now I have the equation for liters. I can plug in the values that I have from above. I have moles of 0.0684 moles. And I'm going to divide by 0.14 molar. And that's going to give me my liters. How many liters do I get?
0.48. 49.
Or 0.49, but yeah. So with two significant figures, it's going to be 0.49 liters. But notice none of the answers is in liters, so I'm going to have to convert to milliliters. And that is going to be 1 milliliter is equal to 1/1000th of a liter, or 1,000 milliliters equals 1 liter, either way. And that's going to give you 490 milliliters. So your answer then is going to be A. So that was kind of complicated. I actually like to use the conversion factor method instead. I'm going to show you how to do the conversion factor method. Notice using the formula still does not make you exempt from using conversions, because using conversions is necessary even when you use the formula. But in this case, if I just take the 4 grams of NaCl, be like, okay, well, I'm just going to convert that to moles. The first step is the same as that of before, 58.44 grams of NaCl is equal to 1 mole. And then I will go ahead and convert moles of NaCl to liters using the molarity, because molarity means moles per liter. So anytime I see 0.14 molar, that's 0.14 moles per 1 liter. Or if it's 5 molar, it's 5 moles per 1 liter. It's always per 1 liter when you're given the molarity. So 0.14 moles is going to be equal to 1 liter. And then I can go ahead and follow that up by converting liters to milliliters. 1 milliliter is equal to 0.001 liters. Or 1,000 milliliters equals 1 liter. Either is fine. So I multiply that by the top, divide by the bottom, and with 2 sig figs, I get the same exact thing. I get 490 milliliters. I think this is much more user-friendly, but you can do it either way. Cool. Just out of curiosity, which one did you prefer? Did you prefer the conversion factor way? Top? Okay. Yeah. It is one of the things I really like about conversion factors is it's very easy to follow once you get the logic of it. Because whatever you have previously on top has to come down and cancel, and then it's a repeated pattern of doing that till you get what you want. Let's look at number 55, because 55 is a slightly different version, slightly different one. Now 55 says, what is the concentration of a solution if 10 milliliters of 3 molar solution of NaOH is diluted to 500 milliliters? The key word is diluted. Anytime you have a situation where you have a dilution, you're going to use the dilution equation, which is, and I'm actually going to write the more general form of it, because this can also be used with percent concentrations, but it's C1 times V1 is equal to C2 times V2. So concentration times volume 1 is equal to concentration 2 times volume 2. And so 1 usually refers to the concentrated solution, and 2 usually refers to the diluted solution. But it doesn't have to. I mean, 1 could be the diluted and 2 could be the concentrated, just as long as you're consistent. For example, if 10 milliliters is my V1, then that means my 3 molar must be my C1, because these two go together. But if 10 milliliters is my V2, then 3 molar must be my C2, because these two have to go together. Doesn't matter if I put them as ones or twos, but they both have to be the same number because they both go together. Does that make sense? We'll go ahead and plug in our numbers here. I'll say my C1 is my initial concentration of 3 molar. My V1 is going to be my initial volume of 10 milliliters. My C2 will be my final concentration. I actually don't know what that is. It's what I'm looking for. And my V2 is my final volume, which is the 500 milliliters. So I'll go ahead and solve this equation for C2, which means I have to get C2 by itself. To get C2 by itself, what do I have to do?
Divide.
Yeah, divide by what? V2. So V2 cancels out, I get C2. So then all I have to do is plug in the numbers here. I have C2 is equal to C1, 3 molar, times V1, which is 10 milliliters, over V2, which is 500 milliliters. Now note one thing. You don't actually have to convert the volume to liters here. As long as the volume unit is the same, which in this case it is because they're both milliliters, as long as the volume unit is the same, it doesn't matter what the volume unit is. This would be gallons for all I care. It's still going to give me the same answer as long as the volume units are the same. So 3 molar times 10 divided by 500, that's going to be what?
0.06.
0.0667. Oh wait, no, not 0.0667, 0.0600 to be precise, because I have 3 significant figures in each one of these cases. Except for the 500.0, that's actually 4 sig figs. So yeah, this is going to be that, which is A. Cool. Now, so if you're asked if you're given concentration, you can use it as a conversion factor. If you're asked to solve for the concentration, either molarity or concentration, you're going to have to actually use the formula. So let's just do one more of these concentration problems because I think it'll be helpful to you. Let's do number 56 because it's the only other one I think type of problem I think could trip you up potentially. It's asking me to solve for the concentration, which means I have to use the formula for the concentration, which is if I have mass percent, that's equal to the grams solute divided by the grams of the solution. times 100%. Okay. So what's the grams of solute in this case? What's the grams of solute?
50.0.
Mm-hmm. Very good, 50.0. The solute is what is being dissolved. Usually that's the lesser amount, the lesser number, although not always. So that's the amount dissolved. Now what is the solution? How many grams of solution do we have? Ah, there we go. Well done, well done. Somebody caught it. The grams of solution is not 150. Solution is the solute and solvent together. Solution is the solute and solvent together. 150 grams is just of the water. So to get the grams of the solution, I actually have to add these together. So this is going to be 150 grams of water plus the 50 grams of NaCl. That's going to give you the total grams of the solution. Don't get caught on those problems. Be very careful in how you read. Because sometimes it will say in 150 grams of solution, in which case you can just put 150 grams. But in this case, it doesn't say grams of solution, it says grams of water. So that's where you have to be careful, and you have to make sure you're reading the problem carefully. In this case, it's going to be 150 plus 50 for the solution. And if you divide that, multiply it times 100%, that's going to give you 25%. Yes.
So if it says solution, then you don't need to add the other part to make it a total?
Exactly, because the solution automatically includes the solute and the solvent. That's already included. But if it just says water, that's not this whole solution. What other problems can I help you with? Avogadro's number? Okay. Let's take a look at one of those problems. Dial ourselves back a bit. Where's Avogadro's number? Come on now. All right, here we go. Here's one. Here's one. Do I have any harder ones? I feel like I want to give you a harder one. That's what I got. I got this one. Let's do 24. I like that one better. All right. It says the following reaction takes place when an electric current is passed through water. Oh, never mind, I lied. Number 24. What is the mass of a thimble of water which contains 4.0 times 10 to the 21 molecules? So there is a general pattern to these types of conversions. And I'd actually like to take a second to show you what this pattern is, because in case you haven't seen it for a while, it's good to understand how these different conversions relate to one another. I want to share this image with you. So this is how mole conversions work. I can convert grams to moles. If I convert grams to moles, I need to use the molar mass. If I convert moles of something to atoms or molecules, and that depends on whether or not it's an element or compound, I have to use Avogadro's number. I can also convert moles to liters using molarity, as we've already shown. Or I can convert moles of one thing to moles of something else. Notice the only way to change the substance, to change one substance to a different substance, is a mole-to-mole ratio. So the only way to go from one thing to a different thing is a mole-to-mole ratio. That's what we do in stoichiometry. But in this case, we're converting molecules of water into mass. It says, what is the mass of a thimble of water that has 4.1 times 10 to the 21st molecules? So that means I'm going to start down here on the bottom left. I'm going to start down here where it says atoms or molecules of A. Okay? I'm then going to use Avogadro's number to convert from atoms or molecules, in this case molecules, to moles. So I have molecules of water. I'm going to use Avogadro's number to convert to moles of water. From moles of water, I can convert to grams of water by using the molar mass. That'll be basically I'm taking that upper left arrow to go from moles of A to grams of A. So this is going to be a two-step conversion. I'm going to convert molecules of water to moles using Avogadro's number, and then moles to grams using the molar mass. So let's go ahead and show what this looks like on paper. Oh, virtual paper anyway. We'll start with our 4.1 times 10 to the 21st molecules, 4.0, my bad, I thought it was 4.1, times 10 to the 21st molecules. And don't abbreviate molecules, MOL. If you do that, shame on you. Moles is not the same thing as molecules. You cannot abbreviate molecules. All right. So I have molecules of water. Water! Here's my little drop of water. A little shadow on it. Molecules of water. What's going to go on top? What can I convert molecules of water to again?
Moles.
I can't convert it to grams. Yeah, there you go. I have to convert it to moles. Very good. So molecules to moles. And what number goes on top? One. 1 mole. And 1 mole is how many molecules? What is that number? That's okay. Remember, to go from moles to molecules, we have to use Avogadro's number, remember? And Avogadro's number is 6.022 times 10 to the 23rd. So moles to molecules is, I'm going to have to use Avogadro's number. So Avogadro's number is the number of molecules in 1 mole of water. Excellent. So now, what unit goes on the bottom of the next conversion factor? If I'm looking for the mass, what unit goes on the bottom of this next conversion factor? Moles. Absolutely. Now, what unit goes on top? What am I trying to convert to? Grams. Very good. I'll put grams of water on top. And how many grams is equal to a mole of water? Where do I need to look? Not 17. 17 is close though. Where do I need to look to get the relationship between grams and moles? Periodic table. Very good. I have 2 hydrogens and 1 oxygen. Oxygen 16, hydrogen is 1. But I have 2 hydrogens, so the molar mass is, yeah, it's 18. If I want to be real precise, I could say it's 18.02. And that's how many grams per 1 mole. So then I just multiply everything on top, divide by everything on bottom, And if I do such a thing, I will end up with what?
How did you get 18.2 again?
18.02. So that comes from the periodic table. Water, I have 1 oxygen, and the molar mass of water is 16.00. And then I have 2 hydrogens, and the molar mass of hydrogen is 1.01. So that gives me 2.02 and 16.00, which if I add them up, gives me a total molar mass of 18.02. And that's going to be 18.02 grams per mole. Does that make sense?
Yes, thank you.
Yeah, no problem. If I multiply everything on top, divide by the bottom, what do I get?
I got 1.96 times 10 to the 45th.
Oh gosh, no.
Oh, okay. I don't know. I think I need more parentheses.
Yeah, okay, so basically what you have to be careful about here is when you're dividing by a number in scientific notation. When you're dividing by a number in scientific notation such as the 6.02 times 10 to the 23rd,
Yeah.
you have to make sure that you put it in parentheses or use the EE button in your calculator. If you have like a, for example, um, if you have a TI or if you have a Casio, sometimes they'll have the TIs will oftentimes have 2 capital E letters next to each other. That's the exponent function. It means times 10 to the power. So to divide by, you would be 6.022 E23. Now, if you divide by 6.022 E23, that would actually, you wouldn't need parentheses for that. But if you're going to put it in full notation like that, if you do 6.022 with the times sign and then 10 raised to the power of 23, you have to make sure you put that in parentheses.
Oh, okay.
And then, yeah, whenever you divide by a number in scientific notation, you must put it in parentheses, otherwise it will not give you the correct answer. Yeah, TI30XS, you can, I'm pretty sure the TI30XS has a EE button on it. Let me look at this. TI, there are cases in which, yeah, see images, TI30XS.
Is it 0.1196?
Yeah, 0.1196 or 0.12. Yeah, so in the TI30XS, there is the exponent button, I think. Oh, wait, no, there's not. Interesting. Okay, that does not have the exponent button. So for the TI30XS, you're going to end up having to just use the little caret symbol, the little upward arrow. Essentially, you'll type in, if I may, you'll do the, you would type in your calculator like this. You basically say 4.0 times sign 10, and then you'd raise little arrow button 21, and then you'd say divided by the divided button, and then you'd have to use parentheses 6.022, and then you'd have to do times 10, little caret button, which means to the power of 23, close parentheses, times 18.02, and then equal sign. Does that give you the correct answer?
Yes, that's how I did it.
Okay, yeah, because I mean, admittedly, having a calculator is great, but you also have to make sure that you know how to get the right notation in to be able to get the answer. And unfortunately, that's not always as easy as we like it to be. Okay, cool. So yeah, 0.12. Shame on me. I originally, I'm kind of evil. I originally put 4.0 times 10 to the 20th for this problem. And in an effort to deliberately give you an answer that's close to but not any of these, if I did 10 to the 20th, it would be 0.012. And then people would be like freaking out because none of the answers is there, but the answer would actually in that case have been none of the above.
Uh,
Wouldn't that be evil if a professor did that? Give you answers similar to the ones that wasn't exactly, so you'd be like, oh, I'm just going to guess, because it's never none of the above, right? Wink. Yeah, shame on me. But no, in this case, it is 0.12. Okay. So, what else can I help you with? And I commend you all for sticking with me because 2 hours of chemistry is a lot of chemistry. I imagine you're probably getting a little burnt out at this point, and you're like, yeah, I'm pretty much ready for this to be over. Oxidation and reduction. Very good, very good. Let's take a look at that. Oxidation and reduction. I'm pretty sure I have a few problems on that. So let's say if I have an equation like this, okay? Let's say I have, I don't know, copper. Yes.
Somebody commented that 26 is a problem.
Ah, okay, well, thank you. I don't have to make up a problem then. Good, because I was feeling lazy and I didn't want to do it anyway. All right, so what is oxidized and what is reduced in the following equation? All right, so if you look at this, there's a few standard rules for oxidation numbers that it's good to have in mind when you're doing a problem like this. And first is, whenever you see an element in its elemental form, it's going to have an oxidation number of what? What is the oxidation number of an element by itself? Okay, so you can think of oxidation number as sort of like internal charge or assigned charge. The actual definition of it is a little bit more complex, but oxidation number effectively is the charge that an atom would have if every shared pair of electrons, the more electronegative atom took the electrons. Okay? So that, like I said, it's a little bit more complicated, but there's a few simple rules that you can use in this case. Any element by itself has no charge, right? There's no charge on aluminum. The oxidation number, therefore, is 0. So for any single atom, or for any substance composed of only one type of element, the oxidation number is typically going to be 0 because the oxidation number has to, the sum of the oxidation numbers has to equal the overall charge of the molecule. So what does that mean? Well, aluminum by itself, the overall charge is 0, so the oxidation number of aluminum is 0. Oxidation number is kind of like internal charge. So what's the oxidation number of Br2?
Would it be 6?
Oh, actually, does Br2 have a charge? Remember, charges will show up as superscripts, right? Those little plus or minuses. Yeah, since it doesn't have a charge, and it's only composed, here's the key point, it's only composed of one element, and it does not have a charge, the oxidation number is going to be 0. Now for an ionic compound, for ions, the oxidation number is the same as the charge of the ion. Well, aluminum bromide is an ionic compound, right? So what is the charge? What is the oxidation number of aluminum? Yeah, the oxidation number of aluminum is a positive 3 because the charge is a positive 3. What is the oxidation number for bromine? -1. Yep. So aluminum's charge is +3, so its oxidation number is +3. Bromine's charge is -1, so its oxidation number is -1. As far as you're concerned, with the types of problems you're going to get, you probably are not going to have to do any of the more complicated oxidation number stuff. So oxidation number for most of what you're going to be dealing with is going to be the same as the charge. So if it's an ionic compound, look for the charges. That'll be your oxidation number. If it's a covalent compound, then it's a little bit more tricky, but usually you're not going to get those. So in this case, you have to understand that a couple different definitions. Oxidation is an increase in charge, an increase in oxidation number, which in most cases is equivalent with charge, at least in your case. Reduction is an increase, or rather not an increase, but a decrease in charge. A decrease in charge, which that's going to, or decrease in oxidation number, which is typically equivalent with charge. So that's the easiest way to think of it. Now, you may have heard in class something like oxidation is gain, or oxidation is losing electrons, reduction is gaining electrons. And while that is true, that in reduction you do gain electrons and in oxidation you do lose electrons, the reason why we call it reduction is not because you gain electrons. That doesn't make any sense. Anytime you've heard reduction in everyday life, it's always something associated with a decrease. So reduction in the workforce is a decrease in the number of jobs. A reduction in pay means you're not getting paid as much. So a reduction is always a decrease in some way. And the reason why it's called reduction is because you're decreasing the charge, you're decreasing the oxidation number. So which one of these has its charge increasing? Which one of these substances has the charge increasing? So bromine going from 0 to -1 is an increase? Yeah, so yeah, aluminum goes from 0 to +3, so the charge increases. Bromine goes from 0 to -1. That's a decrease in charge, or making more negative or a decrease in charge. So bromine is reduced and aluminum is oxidized. So bromine goes from 0 to -1. That is reduced. And aluminum goes from 0 to +3. That is oxidized. Now notice that aluminum bromide is neither oxidized nor reduced. Aluminum bromide is the product of oxidation and reduction. So only reactants can be considered to have been oxidized or reduced. Products are the result of oxidation and reduction. That's an important distinction.
For number 72, could you explain how exactly we would know if it's a strong acid or which one is a strong acid?
Sure. So, unfortunately, you have to have the strong acids memorized. Okay? That is a requirement. You are going to have the strong acids memorized. But there's only 7 of them, so I'm going to go ahead and list them here. So strong acid. Anything that's not a strong acid is by necessity a weak acid. So here's your 7 strong acids. There is HCl, there's HBr, there's HI. There's also HNO3, HClO3, HClO4. And last but not least, H2SO4, sulfuric acid, which is the only polyatomic or diprotic strong acid. It has 2 acidic hydrogens. If you look at these, which one of the 5 choices given is this strong acid? Yeah. B. Yeah, I wish I could say it wasn't, there's a trick to it or something, but unfortunately it's just a matter of memorizing the strong acids, knowing what they are. And most professors do expect you to have those memorized. All right, what else can I help you? Okay, sure. Let's take a look at 73. 73, there's 2 ways to do this problem. There's what I like to call the easy way, and then there's the hard way. I'm going to show you the easy way because, to be honest with you, there's not a whole lot of time left in the session. And at this point, if you don't really have this mastered, the hard way might just get you in more trouble. But basically, the easy way to do this problem is to use what I like to refer to as the titration equation. It's very similar to the dilution equation. So the titration equation is the molarity of the acid times the volume of the acid times the number of acidic hydrogens in the acid is equal to the molarity of the base times the volume of the base times the number of OH minuses in the base. So in this case, it's looking for the concentration of the sodium hydroxide solution. What's the molarity of the acid here? What's the molarity of the acid? Yeah, 2.0 molar. I have 2.0 molar of that H2SO4. What is the volume of the acid? How much do we got? 20, yep. My handwriting is terrible today. 20.0 milliliters. And what is, how many acidic hydrogens are in sulfuric acid? The number of acidic hydrogens, number of H pluses in sulfuric acid. 2, yep. If I look at the formula, I see that it's H2. There's 2 acidic hydrogens. And the acidic hydrogens are always kind of put up in front. If it was H3PO4, then it would be 3 acidic hydrogens. If it's HCl, it would be 1 hydrogen. The only time where it might seem a little tricky is if you had like something like HC2H3O2. In this case, even though there's 4 hydrogens total in the acid, there's only 1 acidic hydrogen. The acidic hydrogens are put out in front. So that's 1 acidic hydrogen. But otherwise, they're pretty easy to tell. So in this case, it is 2. All right, so now, what's the molarity of the base? Well, that's what we're looking for, right? And what's the volume of the base? Yep, 10 milliliters. And how many OH minuses are in sodium hydroxide, are in the formula of sodium hydroxide? How many OH minuses are there? 1. NaOH has 1 OH. So this is just 1. Now, if it was calcium hydroxide, if it was CaOH2, Well, then it would be 2 hydroxides. It would be 2, but in this case it's sodium hydroxide, so it's just 1. Okay, so now all I have to do is solve for the molarity of the base, and I can do that by dividing both sides by 10 milliliters. And 1, of course, I don't really need to divide by the 1, but you know, I divide both sides by 10 milliliters. And that's going to give me my answer. So yeah, you should end up getting about 8 molar. Yep, exactly. The hard way would involve writing the chemical reaction for this equation, or writing the chemical reaction, balancing the chemical reaction, doing some stoichiometry, and using the molarity formula. Do you want to do all that? I didn't think so. Like, no. All right, what else can I help you with? Got 15 more minutes, roughly. What other questions can I go over with you? 87, okay. Let's take a look at 87. 87, it says, which of the following combinations could be used as a buffer? Ooh, good question. So, for something to be a buffer, it has to be composed. For something to be a buffer, it has to be composed of a weak acid and a weak conjugate base. So, weak acid and a weak conjugate base. So a weak acid and its conjugate base. So if I look at this, which could not be used as a buffer? So if I'm looking at this, look at A. What is this a weak acid or a strong acid? This is where we have to remember our weak acids or strong acids. This is actually a weak acid. HNO3 is a weak acid. I mean, HNO3 is a strong acid. HNO2 is a weak acid. The number of oxygens does matter. So this is a weak acid. NO2 minus would be the strong base, so that's a buffer. That's a good buffer. What about HCN? Is HCN a weak acid or a strong acid? Yeah, it's a weak acid. So that would be a decent buffer because CN minus is a weak base. It's the weak conjugate base of HCN. Anytime you take a hydrogen away from a weak acid, it becomes a weak base. All right, what about HCl? Is that a weak acid or a strong acid? Yeah, that one's strong, which means its conjugate base really is actually so weak that it's effectively neutral. It has no basicity whatsoever. Could you use hydrochloric acid and Cl minus as a buffer? What do you think? Yes or no? No. Yeah, a strong acid and its conjugate are not going to be useful as a buffer. So that is not a good base. That's not a good buffer. Not a good buffer. D would also be a good buffer. Acetic acid is weak. Acetate's good conjugate weak base. So there we go. Good deal. Now, somebody wanted to go through problem number 53. So we'll go ahead and jump up to that. So How many equivalents are present in 5 grams of aluminum? Okay, so this requires you to kind of know what the definition of equivalent is. An equivalent is a mole of charge. An equivalent is a mole of charge, not necessarily even positive or negative, but it's just a mole of charge generically. So 5 grams of aluminum, but what I could do is, and I won't take much time with this because I don't know if your professor will cover this or not. It may or may not. I'm leaning towards thinking they probably won't. It really just depends upon the professor, but grams of aluminum, 3 plus. I can convert grams of aluminum to moles of aluminum, 3 plus. And remember that electrons really don't weigh that much, so that it's not going to affect the molar mass here. 1 mole of aluminum is still going to be roughly about 27.0 grams, or 26.98. You want to be real precise. And then you just have to recognize that since an equivalent is a mole of charge, I can say 1 mole of aluminum, Al3 plus, is going to be 3 equivalents, because there's 3 moles, or there's 1 mole of aluminum, there's 3 plus 3 charge, so 1 mole times 3, that's 3 moles of charge. So 3 moles of charge means it's 3 equivalents. And that's it. Like I said, this probably won't be something that's covered, but some professors do cover it, so I did include it. But yeah. So what else can I go over? The answer, by the way, would be A, 0.56. What other questions can I go over with you? Naming molecules. Okay. Cool, yeah, we can do that. Where do I have naming? Actually, I think I might have that at the very end. Oh, come now. I know I have naming. Oh, do you mean like organic naming, or do you mean like, what kind of naming do you mean? Number 106? Okay. 106. 106, okay, number 106, it says, a radioactive element has a half-life of 2 hours. How many hours will it take for the number of atoms to decay to 1/16 of the initial value? Okay, so here's what you have to recognize about half-life. Half-life is the time it takes for half of a substance to decay. So I can cycle this through a series of half-lives. Let's say I start with the whole amount, which I'll represent as 1. After 1 half-life, half remains, right? After a second half-life, I take half of that. So how much remains after a second half-life? Yeah, 0.25 or 1/4, right? After a third half-life, how much remains? 1/8, yep. And then after a fourth half-life, how much remains? Mm-hmm, 1/16. So to get down to 1/16, that means I need 4 half-lives. And if you remember that each half-life is 2 hours, so here's 2 hours, here's 2 hours, here's 2 hours, here's 2 hours. So if I cycle this through, that's 2 plus 2 plus 2 plus 2, that's 8 hours. So it's going to take 8 hours to decay to 1/16 of the original value. So the answer is going to be B. What else can I go over? I can hit at least 1 or 2 more questions. You want to do any organic naming or writing of formula? A few on the back. The last page? Sure. So last page, here we go. It says, let's go ahead and give the IUPAC or common names for each of the following compounds. So I like esters. Let's do number 109, the ester. So for esters, you're going to actually do this by actually breaking this apart into two pieces. So one on one side of the oxygen and one on the other side of the oxygen. One thing that I like to do here is to maybe put little dots in these skeletal formulas. I put little dots where each of the carbons are. That kind of helps me to keep track of which one is, or how many carbons I actually have here. Now, the more important side, I call it the more important. I guess, strictly speaking, it may not be a more important or less important side, but the more important side gets the ending of an ester. And the ending of an ester is 08. The ending of an ester is 08. O-A-T-E. O-A-T-E. That's the ending of an ester. And the more important side is the one with the carbonyl, the one with the double bond O. So in this case, I have a 5-carbon group on the left-hand side with the carbonyl. What is a 5-carbon chain usually called? Penta or pentane. Because this is an ester, I'm going to call this 5-carbon more important group. I'm going to call this pentan 08. Normally it's pentane. I'm going to call it pentan 08. Now the less important side gets named just as if it was just a little branch off the side. And this is going to be methyl. Because it's a 1-carbon branch to the methyl. So then the final name of this compound is actually going to be called, I'll put the less important side first, methyl. And what's really odd here is I'm actually going to put a space. I normally don't put spaces in the name, but for esters and ethers I can. So for esters I'll put methyl pentanoate. Okay. Now if I compare that to the ether below, I actually do something similar in that I circle both sides of the oxygen. Or square both sides of the oxygen, that may be the case. I can also put my little red dots in, indicating where the carbons are. Now a 1-carbon branch, in this case with an ether, they're both just named like branches for the common naming system. The common naming system, they're both just named like branches, so it would be a methyl on the right side and an ethyl, 2-carbon branch would be an ethyl on the left side. So for the common name for this one, I would call this, I just list them in alphabetical order. It would just be ethyl, methyl, ether. Ethyl, methyl, ether. Okay? Ethyl, methyl, ether. That's all you'd have to say for that one. Alternatively, you could put the IUPAC name. Some professors want you to know it. Some professors don't really care. But in IUPAC name, I would simply call this methoxyethane. The longer chain gets treated as if it's just an alkane group. And then the shorter side with the oxygen gets an oxy ending. So methyl, instead of methyl, would be methoxy. And then the longer one would just be ethane. And usually you would put the number like 1 methoxyethane. But the truth is, in this case, there's no other choice. It has to be on 1, because whichever carbon is connected to the substituent would get the number 1 in an ethyl group, because there's only 2 carbons. So you can call it methoxyethane or ethyl methyl ether. Usually professors just have you do the common name. Shall we do one more? What do you think? 113? Ah, this is the amide. So the cool thing about this is that it's actually very similar to the ester. We're gonna once again we're gonna kind of circle both sides of the chain interrupter. And chain interrupter, basically whatever atoms in the middle of the chain, cutting the carbon chain in two. Up here it was an oxygen that was in the middle of the carbon chain. Here there's a nitrogen in the middle of the carbon chain. I circle the groups on either side. Now once again, the more important side is the one with the double bond O, the one with the carbonyl here. So I will start, and I always start numbering. If I had a branch off of this, I would always start numbering from the side of this that's closest to the nitrogen. So this would be 1, 2, 3, 4. Or if I had a branch on the other side, I would have to number it 1, 2. I start numbering closest to the nitrogen. But in this case, I don't have any branches off of either the more important or the less important side. So this would just be, I would name the more important side with an amide ending. So the ending for amide, ending for an ester was 08. The ending for an amide is simply amide. Well, that's easy to remember. Ending for amide is amide. The 4 carbon on the more important side is a 4 carbon amide. So this would just be called what? Yeah, butanamide, exactly. So this is butanamide. And then the other side is just a 2 carbon group, so this would be an ethyl. An ethyl. And you could put the dots there too if you wanted to. It's not necessary. I'll just highlight the answers from the previous problem so you realize it's not relevant to this problem. Okay, so I have butanamide and an ethyl. Now the difference between an ester and an amide is this. There's no spaces. And this doesn't necessarily have to be anything attached to the nitrogen on the other side. It doesn't have to be a less important side for the nitrogen. So when there is a carbon group attached to that nitrogen, I have to indicate its chain. I use a chain locator. Basically, normally have like 1 methyl or 1 chlorobutane or something like that. And you put a number to indicate where it is. But because this is attached to the nitrogen, I'm actually going to say N. So this would be N-ethyl. N-ethyl butanamide, no space. N-ethyl butanamide. And that's it. Well, it looks like we've run out of time, but I hope this was helpful. The entire answer key for this entire massive test is up on the website. I also sent it to you in the email. Feel free to check out some of the other resources on the website, including the video tutorial library. There's lots of excellent tutorial videos on every single topic from all semester long. So feel free to check out the video tutorial library. Just in case you don't remember, the I always sent it in the email, the link to where you can find the video. I am recording this, and so I will post the recording of this. We'll post the recording of this up on our website. I'll also probably email it out to you. Here's the link, putting it in the chat. Here's the link to the web. The resource page. Oh, you're very welcome. You're very welcome. Alternatively, if you are watching this, another way to get to our resource website with the video tutorials is simply Google, or like use whatever your browser is. You use Bing, Brave, whatever. You can just Google TCC SE science, and if you Google that, or if you DuckDuckGo or whatever, put that in your search engine, TCC SE science, you will find our web page. It'll be a Google site. You'll be able to select it and go to Chemistry Web Resources, Chem 1406, and you'll be able to get all the practice tests, practice problems, video tutorials, etc. Thanks so much for coming. I wish you all the best in your final. Hope you all knock it out of the park. And have a great day.